20, we got 15 minutes. Right, what's on the menu? I've got an arithmetic circuits question, I've got a locks question, I've got a clocks question. I'm hearing clocks. Let's do a clocks question. Here we go. Shout loudest, get soonest. Okay. So this is a what the hell does it do question, rather than a build me a thing that does this question. But they do happen. So it starts off with, you know, please collect this mark part, right? What's the characteristic table for a D flip-flop? Well, you give the control signals at time t, and you say how that gives the new state of the flip-flop. And for D flip-flops, it's dead easy, because the new state of the flip-flop is whatever the old control signal was. Okay. Now, there we get this funny little diagram of a half adder connected to a D flip-flop. You can see the half adder gets two inputs, one of which is from this external source X, and the other of which is looped back from the flip-flop. Meanwhile, the ones output of the half adder goes to some output Y, and the twos output is going to be the next thing in the flip-flop. Okay, so we're asked to explain what on earth is going to happen. So yeah, if you wanted some arithmetic circuits, you're getting some, as well as some clocks. Right. So what's going to happen is going to depend on the current input X and the current state of the flip-flop. So what we're being asked to do is to fill in this truth table. So possible situations are these. Okay? Right. So what's controlling, what's giving, so if we know X of t and Q of t, then we know the inputs to the half adder. The outputs to the half adder end up in, respectively, the twos ends up in D of t, and the ones end up in Y. So what you're really being asked in the next two columns is for the truth table for a half adder. Nothing weird about that, eh? So, what goes here on the top for D and Y on this row? Yeah, 0 plus 0 is 0. Okay, what's on the next row? 0 and 1. And on the next row? Well, 1 plus 0 is also, yeah, 0 and 1 makes 1. And how about 1 and 1? That's 2, which is 1, 0. Right. Many, many, many of you have in the past told me that 1 plus 1 is 3. It's an easy mistake to make. Double check that you're not making it. If something goes, so some kind of adding circuit, last row, it's always 3, isn't it? No, it isn't. So just be careful. Okay, and now that we know what D of t is, our characteristic table should tell us what Q of t plus 1 is. What goes in this column? It's the same as D, yeah? This tells us that Q of t plus 1 is always the same as D of t. So, 0, 0, 0, 1. Okay, so what's happening is that at each tick of the clock, we do another bit's worth of adding, and what happens is that the ones from that adding goes to the outputs, and the 2's, that is to say, the carry from that, is remembered by the flip-flop and is added along next time. That's to say, what we are doing is adding to a number that arrives on the X input one bit at a time. First the 1's, then the 2's, then the 4's, and so on. And the flip-flop is being used to remember the carry from the 1's through to the 2's, from the 2's through to the 4's, and so on. And you can see that, well, we'll see in a moment. Okay, next we are asked to convert the truth table from part B into a characteristic table, expressing next state and output in terms of current state. Okay, so how do you do that? You take the truth table 2 at a time, 2 rows at a time. You remove the column for Q of t. So we'll just have columns for y of t and q of t plus 1. We don't need d of t because that's internal. But we are allowed to write formulae here in terms of q of t. Okay? So x is either 0 or 1. To see what happens, we split into the lines where x is 0 and the lines where x is 1. And we look at how q changes. What formula describes what formula expresses q of t plus 1 in terms of q of t here? 0. Q of t plus 1 is always 0. And how about the formula that expresses y? Well, that's just the same as q of t. You can see, whenever q of t is 0, we get 0. Whenever q of t is 1, we get 1. That means we always get q of t. Okay? Let's do the other ones. When we have this q of t, what y do we get? Yeah, that's not q of t. And when we have this q of t, what q of t plus 1 do we get? Q of t. So it's interesting that what we've got here is, in terms of what happens to q of t, it either stays the same or it becomes 0. And then once it has become 0, well, it'll either stay the same or become 0, which means it will always be 0 forevermore. So what we have in fact built is a Tamagotchi. Do you remember Tamagotchis? They were essentially devices that were introduced to teach us how to look after mobile phones. You know, all they said was, feed me or I'll die, feed me or I'll die, oh, I'm dead now. Without doing any other stuff like, you know, enabling you to communicate. But, you know, the basic, can you look after an electronic device by feeding it so it doesn't die? That's what we got here. So you can think of q of t as telling you whether what being 1 as I'm still alive. And okay. So what we're asked in the last part of the question is two things. We're asked we're asked just to say what's going to happen if we feed in some particular inputs. You can see we start off with the Tamagotchi alive, and then in comes a sequence of bits, and we've written down the right rules to explain how to give the output at each step and how to evolve the state. I'm actually going to zoom out a little bit further because it's possibly easier to see this from the truth table. Okay, So if x is 1 and q is 1, what will the output be? So the output's this column. So the output will be 0. And the new state you can read off from this column will be 1. So that goes in the q column on the next line. Everyone see what's going on? Just using the truth table as a cheat sheet. Okay, next we have 0 and 1, so we look up, 0 and 1. That tells us that the output should be 1, and the next state should be 0. So we fill in 1, 0. Okay, Tamagotchi's dead. Fine. We fill in, we've got 2 zeros now. X and q are both 0, y and q of t plus 1 are both 0. Okay, last line, x and q are 1 and 0, output is 1. Okay, so what's going on? If I turn the page sideways, what number did we send in on the x input? Yeah, that's 9. What number came out on the y output? 10. That is to say, because the flip-flop kicked off with an initial carry of 1, its job was effectively to add 1 to the input. And the thing stayed alive while it had to keep carrying. But once a 0 came in on the input, it was able to add the 1, at which point its work was done. Okay, so keeping the page turned sideways, the last part of the question asks you to figure out, given that the initial state of the flip-flop was 1 and the output was this sequence, what must the input have been and what must have been the intermediate states of the flip-flop? Well, what number is this? So what number must we have put in? 7. So that's 1, 1, 1, 0 starting at the little end. And then we can read off from the rules what's going to have happened. Will we have kept carrying? Yes. All the way along, but we'll have carried everywhere, I think. Yeah, so it's 1 and 1 always gives a 0 and 1 coming up. See, 1 and 1 gives us an output of 0 and a carry. Okay, folks. So that's a bit of clocks, a bit of arithmetic. Right. One last thing. We'll try, as I said, we'll try and get as many scores to you this afternoon as possible. You have your tutorial homework where you have an opportunity. Please choose to do, you've got a choice of all topics, but please choose to do the topics that will make the biggest difference, where a tutorial will make the biggest difference to you. Don't just do the ones you find easiest. In fact, do the ones where you need a bit of help to make a difference. Okay, remember, you're not scored on how well you do, you're just scored for having a go. Alright? So with that, thank you very much for a lovely term. And can I have one last 1-minute paper in the boxes, please? Thank you, that almost never happens.